All right, go ahead and get started here. We're going to spend most of today on covalent compounds, talking about what do we do when we don't have a positive ion and a negative ion at the same time. How can we still make everything more stable? And we'll get into how Lewistop structures actually show up and can help us predict what the structure of some of these compounds are. And then I have all the quiz questions from this, not all the quiz questions, most of the quiz questions from this week up here. We'll go through a few of the random ones and then some relevant ones, and we'll save some for Thursday. Somebody asked a good question about biodiversity. There's a lot of species going extinct, and there's a real lack of biodiversity in terms of agriculture. Agriculture is probably the #1 leading cause of the loss of biodiversity, meaning the number of species that are present at any given time in an area, in an ecology. So agriculture is a big problem for biodiversity because we tend to grow a few crops that grow really well, that sell really well, that are resistant to disease and things like that. It probably doesn't affect how many viruses and different illnesses we see necessarily, but it means that they can be a bigger deal. If we only have, so I looked up some numbers for this, and so half of all of the food crops on the planet are one of 4 crops. They're either wheat, rice, corn, or I'm missing the last one, soybeans. And so if half of the food grown worldwide is only 4 different species, if there was a really drastic infection or pest that caused one of those 4 to be completely wiped out, that's got to have a huge impact on people's ability to eat and not die of starvation and all those kind of things that we like to see worldwide. So it means that the lack of biodiversity means that our ecology is a lot more fragile and a lot more subject to getting disrupted, because all of a sudden, if you have a chair that has 6 legs and you take away 2 of the legs, you still have a stable chair, right? But if you have a stool with only 3 legs and you take away one of those, it's no longer stable anymore, right? So the lack of biodiversity is a really big problem that way, but I don't think it affects how many different viruses we see, especially not as humans. Just the ones that we do see tend to be more detrimental, especially when it comes to food chain.
Yeah, example on a small scale is like a long time ago, pretty much all the grapes in Europe died of a blight. So all those varieties just gone. So they had to import a bunch of the American grapes.
Right, yeah, so they had previously taken a bunch of the French wine grapes and transplanted them into the Western Hemisphere, and then when they had that blight, they were able to bring them back. But even better than that is usually if you have more than one food source, because it's basically what Ireland ran into in the potato famine in the mid-1800s. Is basically Ireland was mostly subsistence farmers that had to grow their own food in addition to working the land for the landowners. And so they basically grew just potatoes for themselves because that's all that they could afford and required very little effort on their part, because then they had to go work the fields that actually produced cash crops for the landowners. And so when the potato famine came through, basically all of their food source was gone. It was one disease that wiped out all of the potatoes in Ireland, because potatoes aren't even a native crop in Ireland. Potatoes came from the Western Hemisphere. And so they only had one variety of potato as well. And so when that happened, you wound up with people starving to death in what was at the time a developed nation, which should have been insulated from that. But because they only had what's called a monoculture crop for their food, it caused really, really big problems. And so that's one of the things that biodiversity affects, and one of the reasons why they're trying to get away from only having one variety, only having one species, growing more than one crop at the same time on the same land. There's a lot of research that suggests that the honeybees dying off is related to the monoculture way that we grow crops, because you have these huge stretches of square miles of land where you only have one plant. And if it's not flowering at a particular time, that makes it really hard for honeybees to go out and collect pollen from something that's not flowering. And they don't entirely understand how the interaction between the bees and the monoculture, but they're pretty conclusively linked. And so there's a lot of things going into how do we undo what we've done agriculturally, but it is a big problem. And so it's worth talking about. And speaking of big problems, if governments don't do anything, will climate change be the ultimate cause of the end of the world? Nah. I mean, maybe for humans, but something will be alive in 1,000 years, probably.
The Earth abides through the ages of man.
Right, there you go. There's enough life on Earth, and bacteria evolves quick enough that probably there will still be bacteria alive in 1,000 years. Maybe not anything larger than, say a large rat, potentially. But it has the potential to be like similar to the asteroid that hit the Earth in terms of the dinosaurs, where almost everything died out except for a few species that then went forth and evolved into a bunch of different species. It has the potential to be something like that. So, and it's not likely that the climate change itself could cause man to die necessarily, but it could cause enough destabilization that it could cause society to fall apart, because you wind up with people needing to be relocated, because something like 80% of the world's population lives within, I want to say 10 meters of sea level, and 4 meters of sea level.
40, I think it's 40. Not 40, but yeah.
There's a very large chunk, either way, a very, very significant chunk of the world's population lives within, X meters of sea level. If sea level goes up 2 meters, which is what all projections are showing right now that it's likely to do in the next 50 years or so, then that's going to displace millions of people, hundreds of millions of people, which have to go somewhere. And they're going to migrate places, and that's going to cause a lot of what they call climate refugees. And refugees destabilize political governments just by the act of coming to a new place to live, just by looking for something better to live. And so you have the potential for a lot of world governments to be destabilized by these climate refugees, by lack of food, because this is also going to really affect our ability to produce enough food for the world. And so you have famine, you have refugees, you have border skirmishes, you have people fighting over where the borders are, because the borders are changing, because water levels are changing. So you have the potential for a lot of really nasty things to happen. So are any one of those things on their own necessarily going to make mankind extinct? Probably not. But there's a potential, especially when you realize that all of those things are happening at the same time. It's a little bit of a 4 horsemen of the apocalypse situation, right? Famine, death, pestilence, and war.
Don't forget conquest.
Conquest was the original that was replaced by pestilence, because they thought conquest and war sounded too similar.
Yeah, I don't know why the heck that was even in there for some reason.
Well, conquest used to be a very different thing than war.
Oh yeah, I guess.
War was the act of the fighting. Conquest was being enslaved.
Oh yeah.
And the people that were doing the translating were well-to-do white men from Europe. So they didn't want people thinking about conquest and slavery too much when these translations were happening, so they replaced conquest with pestilence. But all that stuff is likely to be an issue. So not the ultimate cause of the end of the world, but maybe for people, difficult to say. It's not good, that's for sure. MSG. MSG gets a bad rap. MSG is delicious.
Yeah, it's also in everything like broccoli and soybeans.
MSG is an essential amino acid, not in the form that it's used in food. MSG stands for monosodium glutamate. Glutamate's an essential amino acid that's in everything that has protein. It gets a bad rap because MSG is actually the compound that actually triggers the taste umami in your tongue and your senses. So it makes things taste meaty and satisfying. And so what was happening in the 70s and 80s is basically really, really cheap places were basically taking water and salt and cornstarch and MSG and calling it a balanced meal. So it had some calories to it. It tasted okay, but they would add so much MSG because it was cheaper than adding real meat, and it didn't have a lot of the same nutrition. You didn't actually have enough protein to sustain you, despite the fact it tasted like it did. So MSG got a bad rap for that, and so that's why you see places advertising no MSG. What they really mean is no MSG added. But some places still use it. Basically, you can have a salt shaker. You've got your salt shaker and your MSG shaker, and you sprinkle some on. Makes it taste really nice. It's just not all that healthy to only get your protein from MSG because it's only one of the 20 amino acids. I think there's either 8 or 12 amino acids you need to get in your diet, and you can make the others. And MSG is one of the ones that you need to eat. But you need the other 7 or 11 as well. So, and then last for random questions today. Aluminum. What's the deal with aluminum and antiperspirants? Is that really bad for you? This is a really good example of correlation versus causation. We know that there have been a lot of studies that show that if you use antiperspirants that have aluminum in them, which is most of the white, opaque antiperspirants that you can get, that's linked to higher chances of having Alzheimer's later in your life. But we can't say that the aluminum causes Alzheimer's because there are a lot of other potential variables. This is a very big study over a lot of different things that are happening, right? So we can say they're correlated. People that use these aluminum-containing antiperspirants are more likely to have Alzheimer's, but we can't say that it's caused by the aluminum. It could be because people that are using these antiperspirants are in America and are of a certain socioeconomic class. And that has some other variable that actually is related to causing Alzheimer's. We know it's connected. We don't know how. I mean, this would be a really weird example, but in theory, you could say, well, it's actually that you're genetically predisposed to Alzheimer's that makes you more likely to buy antiperspirant. That doesn't really make a whole lot of sense, but we don't really have any argument saying that can't happen, that that's not what's going on. We just know that these studies show that both of those two things are linked. So I don't wear deodorant with that aluminum antiperspirant in it because I don't really want to test that. Alzheimer's doesn't seem like a particularly fun disease. It's the line from Waiting, right? Alzheimer's isn't all bad. Get to meet new people every day. Seems like I'm making light of it, but it doesn't seem like a very fun disease. So I'm not really taking that much in the way of chances with it. But at the same time, we can't conclusively say that it's caused by the aluminum. And really, it's not just aluminum. It's aluminum that's linked to organic compounds specifically. So aluminum cans had no effect. There's no correlation there. Or aluminum water bottles doesn't have any effect. It's specifically aluminum that's linked to organic compounds that causes something, potentially causes, I used the word cause, that just had that big talk about correlation and causation. So I don't use that stuff because I don't really want to test that, but we can't conclusively say it one way or the other. But good question. I think we're going at about the right pace because roughly half the questions were relevant to the stuff we're talking about and half the questions were random stuff. If everybody is asking questions and is confused by the stuff we've been going over, then we're probably going too fast. And if I'm only getting really random questions, then I'm going too slow. So this is always a good one, right? And when you're not sure what to put for your question, why the heck does any of the stuff we're learning right now matter? It's a big deal because it's basically one step removed from pure quantum and counting protons, neutrons, and electrons. So we're based atomic radius, ionization energy, electronegativity. If you're a doctor, is any of this specifically going to be something you're going to use on an everyday basis? No. But we're sort of building up layers of understanding, starting at the bare bones of this is what an orbital is, this is what a proton is, and building up layers of understanding. So you get to the point where once we know what electronegativity is, you guys can understand what organic chemistry is and how it works. Once you understand organic chemistry, you can understand biochemistry. Once you understand biochemistry, you can understand modern medicine. So, but you can't really understand organic chemistry unless you know how atomic radius and electronegativity work and how they're affected by orbitals, right? So it's not necessarily that this stuff is something you personally are ever going to use again once you get through your schooling, but you're not going to be able to understand your schooling unless you understand this stuff, right? So we call it foundational knowledge. 2 plus 2, right? Exactly. You can't do algebra if you don't know 2 plus 2. It's a good analogy for it. What do we do with the D block when it comes to deciding charge? Well, basically, if it's not one of those 6 that we called out specifically as having always the same charge as an ion, we don't know what to do with anything from column 3 over. So all of these, other than the 6 that we called out, have multiple possible charges, and we basically just need to specify what the charge is. And I don't expect you to be able to know off the top of your head what are the 2 possible charges for iron and what's most stable. If you have the right periodic table that has +2 or +3 written on there, but that's not the periodic table that you have on the test. So with that in mind, I'm not going to assume that you know what the possible charges are for anything. You don't have to have them memorized. Some of the more common ones like iron and copper, you will wind up memorizing just because we'll use them all the time. Copper can be +1 or +2. +2 is more stable. Iron can be +2 or +3. +3 is more stable. I only know that because I've been doing this for a long time. As far as the logic for why that's the case, it's always going to come down to those electron configurations in the molecular orbitals. But again, those energy levels get so close together and they fluctuate enough that I'm not going to expect you to be able to replicate that from memory on test. Does the crisscross method of figuring out ionic compounds always work? Yes, if you then reduce your coefficients to the lowest whole number ratio. So remember, the crisscross method was the one where if you say, okay, iron has a +3 charge, oxygen has a 2- charge, what's the formula going to be? So the crisscross method would just be say, well, take that number and put it there, and take that number and put it there. And that makes the charges work out. But what about if you have magnesium oxide? 2 and a 2, right? So that would say that your formula would be Mg2O2. That's not the smallest whole number ratio. If you take this and then you reduce it to 1 and 1, and you don't have to write the ones, but just for the sake of showing it right now I am, then yes, the crisscross method always works. You just have to remember to reduce it. And a lot of times, for some people who struggled with things like lowest common denominator or least common multiple, the idea of reducing fractions and ratios is scarier than just making the charges add up to 0. So it's totally your call. Just make sure you don't leave it as Mg2O2. Use that crisscross method. This was a good one. Do electrons increase speed or angular momentum as they enter higher energy levels? That's an interesting one because it's actually the opposite in orbital dynamics. If you look at orbital dynamics of satellites and rockets, the higher something is in orbit, the slower it's going. It has more potential energy once it gets higher up above the surface, but it actually is moving slower. And that's actually how you get geosynchronous satellites. Geosynchronous means it never moves relative to the surface of the Earth. If you place a satellite at exactly the right height, then its speed is the same as the Earth's rotation. And so you wind up basically with a satellite sitting above the same point on Earth at all times. And so if you go higher than that, then you actually wind up with the satellite going slower than the Earth is rotating. If you're lower than that, it's actually moving faster than the Earth is rotating.
Where did the SpaceX thing fall on that?
So low Earth orbit is lower than geosynchronous satellites. I want to say geosynchronous satellites are something like, I'm going to mix this up because I played too much Kerbal Space Program a few years ago, and all the numbers are different. I think it might be 250 kilometers above the surface for Kerbal Space Program, which means it's something like 600 kilometers above the surface for Earth. If you are at all interested in rocket science, I highly recommend that game. It basically forces you to learn rocket science under the guise of putting little cartoon guys in orbit.
Hey, you know they made a sequel?
They're on there. Yeah, there might be released. I haven't played that one yet.
Released it yet or not?
I'm not interested at the moment because I don't have enough time to sink another 1,000 hours into learning a video game. So I will be avoiding that one. So electrons don't actually behave that way, but if they behaved as though it was a satellite, they would actually be going slower as you got to the higher energy levels. Because we're talking about higher potential energy levels, not kinetic energy levels. And then one more time, just like up here, right? Same question, but opposite. What's the understanding? Why do we need to understand the difference between homogeneous and heterogeneous? It's sort of one of those things that you need to understand how the world actually works. The difference between homogeneous mixture and heterogeneous mixture is the difference between making the assumption that everything is uniformly mixed and the way it actually behaves. And you can wind up with issues like if you're administering medication to somebody, if you don't know that it's a heterogeneous mixture because it all settles to the bottom, you could wind up giving somebody an overdose because you didn't shake it up before you pulled the sample from it, right? Before you pulled the dose out. So just understanding, it's basically an understanding of just this is the way the real world behaves. Understanding that a heterogeneous mixture is a thing. We'll do a lot in this class where we assume things are homogeneous mixture because it's convenient and usually accurate within sig figs. That's not always the case. So we need to understand where that assumption breaks down. And then chemistry meme, since we're talking about quantum. Okay, electron's a wave, then you observe it. Well, now I'm not doing it. That's basically how electrons act. They act like a petulant 4-year-old. No, I'm not a trained monkey. You can't make me act like a wave unless you don't observe me. All right, let's do some review of ionic compounds. Determine the charge on each ion and name the following compounds. Remember, if it's an ion that has more than one possible charge, you need to specify what the charge is on that metal ion. We'll go through them first. Barium and sulfide both have well-known charges where they're the same charge every time, basically. So Barium's in column 2, so it has 2 electrons to give up, so the barium's going to be 2 plus. The sulfur needs to gain 2 electrons to be stable, so because it's in column 16 right here, so it needs to gain 2 electrons, so the sulfur is going to be 2 minus. But since both of these will always have the same charge in an ionic compound, we don't need to specify the charge in our name. We can just say barium sulfide. Right? Anytime you don't need to specify the charge, it's just the name of the metal, the name of the anion. If it's an element that has multiple possible charges, like iron, we don't know what the charge is on the iron, but we know what chloride is. Chloride always has to be -1, because it has to gain 1 electron to become stable. It has to gain 1 electron to have a full valence.
Couldn't it also the half full thing too? If you do a +2 for
For the p orbital, the half full is not usually going to be stable enough. We actually observe those elements as existing in that state. It'll either go to all the way full or all the way empty. And if chlorine's all the way over here in column 17, it's way more likely to gain 1 electron than it is to lose 7 electrons. So those keeping it exactly halfway full matters, especially for the d orbital, but it's not something where we're actually going to see it sit at a charge of, say, +2.
Okay, so phosphorus, what's more stable charge?
So it can either lose 3 or really lose 5, because it wants to empty the entire energy level, or it can gain 3. So if your choice is lose 5 or gain 3, it's going to gain 3. Remember, this stair-step line, our line separating our metals from non-metals, is what we're going to use as our number 1 rule for differentiating between something that wants to gain electrons or lose electrons. Anything that's a non-metal is going to try to gain electrons. Anything that's a metal that's left and below this line is going to try to lose electrons to become stable.
Carbon, for example.
Carbon, for example. Well, we'll talk about what happens with non-metals. The further you get away from having a completely filled orbital to start with, the harder it is. So carbon can gain 4 electrons, or it can lose 4 electrons. But realistically, carbon is in a spot where it actually winds up sharing electrons more than actually gaining or losing electrons. That's what we're talking about today.
Okay.
So hold your thought on carbon. Things that are close to the edge, though, we're just going to give them enough electrons to get to having a full energy level. Right? So chlorine needs to gain 1 electron to have a full energy level. So we know that these chlorides are each -1, and there's 3 of them. And there's 1 iron, so what does the charge on iron have to be? +3, right? You need them to add up to 0. So the name of this compound, so iron would be 3 plus, and the name would then be iron 3 chloride. And again, if you don't remember how Roman numerals work, I'm not going to mark you down if you wrote it like this. It's just not as commonly seen. It's basically, the reason we use Roman numerals here is to differentiate between writing it this way and saying it's subscript. Right, so we only really use Roman numerals when we're talking specifically about charges.
Just to avoid confusion, there aren't 3 irons.
Exactly.
What's the charge about?
Right, and that's the other thing we do is we make sure that you don't say, you're either saying the formula or saying the name. Never mix and match. If you're saying the atomic symbols, then any numbers that you throw in there are subscripts. So you can say FeCl3, or you can say iron 3 chloride. You don't mix and match the name and the formula, because that leads us to getting really confused about, well, was that 3 the charge, or was that how many you have? If you're saying the formula, then the number is how many you have. If you're saying the name, the number is the charge. Right, so it'll take some practice. We'll get there.
Eventually, the light bulb will go off, though, because of right now it's very
PDI4.
Lead, iodide.
So our basic name is going to be lead iodide. Then we need to specify the charge on lead because lead can have more than one possible charge.
Lead 4.
So because we know that iodide, you're correct, but we'll go through the logic. So we don't know what the charge is on lead, but we know iodide is in the same column as chlorine, right? So it also just needs to gain 1 electron to have a full energy level.
Okay.
So that tells us that iodide is a -1 charge. And there's 4 of them. Because that's what that's telling us. So the charge on the lead, to make it add up to a charge, an overall neutral compound, lead has to be +4. Because +4 from the lead and 4 -1s adds up to 0. So our name of our compound would be lead 4 iodide. What are our 2 ions for D?
That's our 2 plus and Ionic.
Bromine, again, same column as chlorine and bromine, right? So bromine's going to be -1 when it becomes bromide, and there's 2 of them. Strontium, therefore, has to be a +2. Do we need to say the number for strontium?
No.
Why not?
Because you don't have a
Because it's always the same charge. Strontium as an ion will always be +2 because it's in column 2 on the periodic table. Right, so if it's always the same charge, you don't need to specify. A strontium ion will always be +2, so you don't say strontium 2. You just say strontium bromide.
Why would you say strontium bromide 2? Because we took 2 of them, just like how we did every other portion. So why is there a Roman numeral after bromide?
Strontium is modified.
So we only use the Roman numerals for the metal ions where we're not sure what the charge is, where they have more than one possible charge
In the D block.
in the D block, basically.
So like these other beryllium would never have a Roman numeral after it.
Correct.
Or magnesium or calcium.
Nothing from column 1 or 2 will ever have a Roman numeral after it. There's always the same charge when it's an ion. It's always +1 or +2. These 6 over here that we went through the electron configuration for, we said, oh, those must be the stable ions, right? They only had one possible charge. Those ones you never have to specify either. You never have to say silver 1 chloride because silver is only ever a +1. Right? But anything else, if it's not one of those 6, or the first 2 columns, any other metal, you have to say the charge.
No, everything to the left of that stairs.
Everything to the left of that stair-step line. Like excluding hydrogen, but hydrogen is always going to be a little bit weird. Right, and so that's the level of that we're going to need to know for nomenclature on the midterm. We're not going to introduce polyatomic ions until after the midterm. And then you'll have a quiz, a memorization quiz on those, but not till after the midterm. Right, so understanding if it's a metal that you don't know, use your Roman numerals. Otherwise, just say the name of each ion. All right, and so there's a flow chart that kind of goes through that logic, but to me, this actually makes it look more complicated than it is. If it's an ionic, it means it's a metal and a non-metal. Something, a positive charge and a negative charge. And we're just going to say the name of each ion. If your metal only forms one type of ion, you just say the name of the metal, name of the non-metal with I at the end, IDE. If the metal forms more than one type of ion, we still do the same thing, we just throw in the charge on the metal in Roman numerals. Right, that's all there is to naming ionic compounds at this point. All right, so now I've been hinting at it and think we've been mentioning this term for a while. What about two nonmetals? What separates metals from nonmetals? That's the stair-step line, but I mean, like, what property makes something a metal versus a nonmetal? Redox. That's a reaction.
The ionization energy, isn't it?
Ionization energy is closer.
Conductivity.
Conductivity gives it metallic character.
Malleability.
Malleability, yeah, all those things. Basically, it always comes down to things to the left of this line want to give away electrons to be more stable. And things to the right want to gain electrons to be more stable. So our nonmetals, if we have two nonmetals making a compound together, they're both trying to gain electrons. If they're both trying to gain electrons at the same time, you're not going to make ionic compounds because you're not going to have a plus charge and a minus charge. All right, so covalent compounds, where you have more than one non-metal together, make what we call molecules. Right, and the logic is you don't need to gain electrons if you share electrons. Non-metals, always thinking. You don't need to gain electrons if you share electrons. And so that's actually what the term covalent means, and I'm going to be completely honest with you. It took me an embarrassingly long amount of time before I actually looked at the word covalent and what it actually means. Covalent literally means in both valences. I just thought it was a vocab term, so I just memorized it, never really broke it down. So I went through all of my education without ever considering that, which is funny because I do that with every other vocab word I run across. I break it down. Oh, it's these two things. Covalent means in both valences. So if we can share electrons, then everything gets to have a full valence. Everything gets to gain enough electrons by sharing to make it more stable. And the easiest way to tell the difference between ionic compounds and covalent compounds is it a metal and a nonmetal or two nonmetals? So if it's ionic, what type is going to give us ionic compounds? What are we going to see?
Non-metal and metal.
Non-metal and metal. You got to have a positive charge and a negative charge, right?
Yeah.
So that's the only one here out of these three. That is an ionic compound because it's a metal and a non-metal. The rest of these all have only non-metals.
Is the first one carbon, fluorine, fluoride?
The first one we would not name using regular, what we call inorganic nomenclature. We'd name that with organic nomenclature, which that would be actually difluorodichloromethane. That's actually the definition of the CFC. CFC is chlorofluorocarbon. So this is actually a refrigerant and a propellant in aerosols from the 70s that's now been banned. Although it still gets used in some countries. Because it turns out we thought it was a really, really good propellant and really, really good refrigerant. But the problem is it's really stable and harmless at sea level. If it gets up into the upper atmosphere, and when it gets hit by UV light, it actually breaks up into free radicals, which then go around and react with all sorts of other things. So this is actually what caused the hole in the ozone layer, was the fact that we thought this was a really cool compound because it was really useful and seemed really stable and healthy to us at sea level. But it basically caused ozone to react and not be ozone anymore once it gets to that upper atmosphere.
Not ideal.
Not ideal. They've actually seen an uptick in skin cancer in penguins because the hole in the ozone layer is centered over Antarctica. So we can actually track skin cancer in penguins as a way to link conclusively the hole in the ozone layer to less than ideal outcomes. Australia too, but skin cancer in humans is not nearly as funny as skin cancer in penguins. Not that that's really that funny either, it just seems weirder.
Yeah. Hey, but at least it'll probably heal by about 2050.
It should be, as long as we do a good job of globally outlawing these chlorofluorocarbons and keeping them from being used. Which is why our refrigerators actually got less efficient for a short while when this was banned. You had to use more electricity, but it was because we weren't using this as a refrigerant or compounds related to this.
What are we using now?
I'd have to double check. Antifreeze, maybe. Ethylene glycol is a lot more stable. It's also a lot more toxic to animals and people, and tastes sweet. So it's, again, a less than ideal combination, but it's way better for the environment.
Doesn't lead also taste sweet, apparently?
Yes. Lots of things are like that.
How do people find out?
Sean, real quick, sorry, just
Oh,
you're
we
just talking
used
about
to
bonds
use
and
lead
stuff.
to titanium.
Because the other ones were just non-metal and non-metals, does it matter how long, like how many elements you have, as long as you have one metal, does that make it an ionic just to have one that cancels it out?
So this is one of those things where I'm going to teach you, this is your general rule, and then next year, if you take OChem, it's going to be, well, remember how I told you that? Well, it's not really the case.
Okay.
Because if you have metals that are close to this line, they actually are fairly electronegative for a metal, and you can actually wind up with covalent bonds between carbon and aluminum, for instance, like the antiperspirant we were talking about earlier. When you can make a covalent bond between a non-metal and a metal, that's one of the reasons why some of these are considered metalloids, because they kind of can make compounds.
Okay. But just for this
For
class, if
this
it's a
class,
metal,
if there's a metal, it's going to be a ionic
no
compound.
matter how many other non-metals were shared.
Correct.
Okay.
One metal is all it takes, because whatever else is attached to the metal is going to be an ion of some sort. And sometimes those can be really big compounds, like if you can have, you make a 6-sided ring, alternating double bonds of carbons, and then you replace, or put a hydrogen around these, and put an acid group over here with a negative charge. This whole thing is one ion called benzoate. So sodium benzoate that gets used as a preservative in a lot of processed foods is an ionic compound where you've got all of this is your negative ion, and sodium ion is your positive ion. Right, so it's still an ionic compound despite the fact we have this big old covalent mess over here. As long as it has one negative, you can make a covalent or an ionic compound with something with a positive.
Can you go over is that sulfate?
That is not sulfate.
Sulfite.
That's not even sulfite because it doesn't have a charge. If it was SO3 with a -2 charge, it would be sulfite. If it's SO3 with no charge, it's a covalent compound. And we're just going to name those. Close. We just use prefixes to say how many we have.
Sulfur monoxide?
It was SO3, right?
Oh, yeah, I mean trioxide.
SO3 is just going to be sulfur trioxide. Right, so these are actually really easy to name once you know these prefixes. Most of these prefixes should seem pretty similar or familiar to you. You might have to brush up on some of them.
Except for mono, I keep wanting to use uni.
Yeah, so not uni, these are the Greek prefixes, not Latin prefixes, with the exception of mono, because I believe mono is Latin, but the rest of these are Greek. So I'm not sure how they arrived at using mono instead of uni, but
Probably no reason.
it's a little arbitrary. I'm sure there was a reason at some point, it's just been lost to the ages.
How does that not have a charge?
So let's talk about that. If we only have enough electrons that we can make all of these add up to 0, then that means we're limited in how we're going to arrange this. So if we have a sulfur has 6 valence electrons, right? And there's 3 oxygens, and they each bring 6 electrons too. So overall, we only have a total of 24 electrons to work with. So the fact that it doesn't have a charge is actually what tells us how the electrons are going to be arranged. Because sulfite that has 2 extra electrons is going to look different. Not just in terms of having a charge, the way that electrons are distributed is going to look different as well. Right, so if we want to figure out how we can do this, we need all of these to have a full valence, but we can only use, at most, 24 electrons total, because we're not going to get into any of the core electrons. So if we have 24 electrons to fill up 4 valences, they're going to have to share. And so the way we go about doing this, and I have a whole slide on this later, so we'll do more practice with this. We're going to put something in the middle and surround it by everything else. In this case, sulfur is less electronegative than oxygen. Therefore, it doesn't pull electrons into itself as tightly. So sulfur is more likely to share than oxygen is. So if we know that all of these compounds have to work together, we know that there has to be a bond between the oxygens and the sulfur.
Is that 2 electrons or is that 1?
So bonds are always going to be 2 electrons because each atom has to contribute 1 electron for these covalent bonds. So each of these, there's 2 electrons, and we can actually draw it as a pair as well.
What's the diagram called?
This is a Lewistop structure. So we just used 6 electrons, right? We only had 24 to begin with, so now we're at 18 electrons left.
So you sort of just fill it in from
We
there?
just fill it in. So how many more electrons does each oxygen need compared to the way it's drawn right now? 6 more, give it a total of 8 electrons in its valence, right, which is stable.
6 by 6 is 1.
And so there goes our first 6. There's another 6 right here. If we count up all the red dots right there, that's 24. We just used all the electrons that we have, and all the oxygens are stable. But we need sulfur to gain 2 more electrons, because sulfur only has 6 electrons, the way it's drawn here, and it wants 8 to be stable. Remember, all of them are trying to get to having a full energy level. So basically what we're going to do is, well, we can't just throw more electrons on there because we already used all 24. If it was sulfite with a -2 charge, we would just have 2 more electrons to work with and we'd be done. If it's sulfur trioxide that's neutral, we basically have to force one of these oxygens to share more than normal.
Okay. So that's where the double bonds come in.
That's where double bonds come in.
Right.
So if you have too few electrons for the number of atoms, you just wind up with them sharing extra. And it's still, oxygen doesn't really want to be sharing that much because it's pulling electrons, it's really strong at pulling electrons towards itself, but it's better than having sulfur with an incomplete valence. All right, and so we'll do lots of practice with this. And that's basically the rest of what we have to cover before the midterm is going to be this and the immediate applications of this. Okay?
So what is a line on
So basically a line represents a pair of electrons that's between 2 atoms. So rather than draw it this way, it's more convenient a lot of times to just draw it like that.
So it like 2 electrons.
It means 2 electrons. It's specifically 2 electrons that are in between 2 nuclei. So we're going to represent these electrons that aren't part of a bond. These are called lone pairs because they're only attached to 1 atom. And we don't represent those with a line. In fact, usually what I'll do so that you don't lose them or forget them that they're there, is I do that because that's roughly the shape of the orbitals that they're sitting in. Right, and so that will show us spatially what we're looking at and remind you. It's really easy, especially if you're doing pencil on a piece of paper, it's really easy to make your dots too fast and forget that you had a pair of electrons there. So doing a little loop around there reminds you that's a pair of electrons. And any of the lines are also a pair of electrons. All right, so a couple of other definitions. For ionic compounds, we had these mostly these solids where we had a huge number. We had, we're talking about moles of ions at a time, of sodium ions and chloride ions or whatever we're talking about. And so we were looking for the lowest whole number ratio of those ions. For molecular compounds, for covalent, and I'm going to use the term molecular and covalent, mean more or less the same thing. Covalent or molecular compounds, the lowest whole number ratio of atoms is not always the shape of the entire molecule. So an empirical formula is just the same thing as we did for ionic compounds. It's the lowest whole number ratio of elements. But the molecular formula is the total number of atoms in a molecule. So here's a fairly simple compound. This is hydrogen peroxide. Its molecular formula is H2O2. This is allowed in covalent compounds. In ionic compounds, this would be a red flag, like we talked about earlier, right? Ionic compounds, we're supposed to reduce this. But in molecular compounds, where we actually have discrete objects, instead of just having this big mass of alternating ions, we're actually going to, the most accurate way of doing this is to write the total number of atoms that are in a molecule, as opposed to reducing this. If you reduce it, that gives you the empirical formula.
It could just be HO.
It would just be HO.
Could it be OH or does it actually matter?
It could be OH, that's fine in that case. For the most part, we're not actually going to use the empirical formula. It's called the empirical formula. Empirical means from experiment. So it's the empirical formula because if you take pure hydrogen peroxide and you break it down, you can count the number of hydrogen atoms and oxygen atoms, and you get a 1-to-1 ratio. But that's not actually how they behave. They actually stick together to make H2O2. So the molecular formula is more accurate, but the empirical formula is what you get your first evidence for. So another good example is acetylene and benzene. Benzene is those alternating double bonds between carbons, like I used earlier for the benzoate. And the formula is C6H6. Acetylene is a carbon triple bonded to another carbon with a hydrogen on each side. That's C2H2. They have the same empirical formula, but they're very, very different in terms of their properties. Right, so if we were just trying to figure out what we had, and we broke it down, we got a 1-to-1 ratio of carbons to hydrogens, that's not enough. The empirical formula is not enough to distinguish between these. We would need more information somehow to be able to say whether we had benzene or acetylene. Right, so it's one of those things where I want you to have seen the term empirical formula, but the molecular formula is much more helpful to know what we're talking about in terms of things like molecular weight of a compound. The empirical formula doesn't tell us the molecular weight of the compound. It tells us a couple possibilities. But unless you know if you have 1 carbon or 2 carbons or 6 carbons, you don't really know what the molecular weight is. You just know the ratio of hydrogens to carbons. And just to cover a few more vocab terms before we take our break, and then we'll come back and do lots of practice with Lewistop structures. If we want to show a molecule's shape beyond just the molecular formula, we need more information, like I mentioned, right? Even if you know that it's acetylene and C2H2, that doesn't necessarily tell you how the atoms are arranged, especially as you get to larger and larger structures. For instance, C6H12O6 is a really important biological compound. Anybody know what it is?
Glucose.
It's glucose. It turns out it's also fructose. The only difference between glucose and fructose is the way the oxygens and the carbons are arranged relative to each other. It's the same formula. So when we need more information than just the formula gives us, then we have to use a structural formula or molecular models. So structural formula is something like this, where you're showing the individual bonds. And so there's other ways of representing these. Here's another example of a structural formula, and this is glucose. I think it might be fructose. The only difference, let's see, in fructose, this carbon-oxygen double bond is here instead of there. This OH and that carbon-oxygen double bond are switched. It matters a little bit in terms of how your enzyme active sites bind to it. So it changed basically your body converts fructose and glucose back and forth at will. Basically, to your body, nutritionally, there's no difference between glucose and fructose. Turns out there are more complicated things happening. So it turns out living organisms are complicated. I'm not sure if you guys have had enough bio to get that one yet. But yes, living things are tricky. They're complicated. It's a lot of moving pieces.
Yeah, they're obscenely complicated.
Very complicated. I'll show you an example of that when we get further along here. These are all different examples of showing the structure. This is called a space filling model because it actually fills in the electron density, so you can actually see roughly the shape of the molecule. This is a little bit easier to tell what atoms are connected where and how they're connected. For instance, you can't see the double bonds here. You can here, right there. This is a lot easier to draw unless you have colored pencils, right? So all of these have their different strengths. And so under different circumstances, we will use them all. And in any case, we want the molecular formula, which is just writing out this way. This is still useful. There's a lot more information in these structures, but this is actually the fastest way to get to your molecular weight, right? You want to know the molecular weight of glucose. You say, well, I've got 6 carbons, 12 hydrogens, and 6 oxygens. Add up all the atomic masses, and you get the molecular mass. Right, so just like we did with water in your ICA from a few weeks ago, and salt, for that matter, in that same ICA. You just add up the pieces. So the molecular formula is still useful, even though these have more information. Right, when you get to OChem, we'll deal almost exclusively with drawing it out like this. For this class, we're going to do a lot with this formula because we're going to practice using molecular weights and doing calculations with those until your eyes bleed. And you can do it in your sleep. So once that happens, then we can get into, well, more complicated structures doing those. All right. Well, let's take a break there. Let's come back at 10 after. And we will keep doing practice with these covalent compounds. Yeah. Right, boron and beryllium. And it was the ones on either side of that too, right? Was it lithium, beryllium?
It was something like that, but yeah, because I got the first one, the last one right, but those two said were opposite, but that didn't make sense with the notes that we had. Or not to me.
So it's because you wind up with ionization energy, the trend winds up being something you have to pay attention to, because if you hit something where you have an exactly full orbital or one electron by itself, that actually is going to throw them off. Remember the sawteeth on that graph? The general trend as you went from left to right looked like that, but really it was I asked you about one of those.
Because I just went off of the notes that was just talking about the ionization energy increases and what like that, like from the largest. So I saw that the top right was the biggest and the bottom left was the smallest. So because that one went from right to left, I was like, okay.
Yeah, so ionization energy,
Had to be
you have to pay attention to the actual orbitals.
That sucks. Because beryllium is a full orbital, it has a higher.
It's harder to break it up
Even though
than
it's in the
boron.
same energy level.
Correct.
So stupid. Alright.
So you went a little too fast for me on the SO3.
Yes.
When you were doing the 66 electrons.
Yes.
Where did you get the 6 from? Is it because it's in all of 2, in all of level 2, there's 6, in all of
Correct.
level 3, there's 6?
Correct.
So you're counting not just the valence electrons, but every electron in that energy level?
Which is the valence electrons.
Okay.
Valence electrons valence shell means what is the highest occupied energy level. So basically, you're absolutely right. I looked at this periodic table and you say, okay, well, oxygen is all the way over here. So in row 2, there's 1, 2, 3, 4, 5, 6 oxygen.
Same with sulfur.
And sulfur as well. It's just in N equals 3.
Now, and then when we started doing the dots though, you only had 3 around us, whereas like usually I would just do 4 around us. But you just did 3 and started filling.
I did because
There's 3 O's?
because there's 3 oxygens, and we'll go over why. But basically, the way I do these is you figure out your total number of electrons you have to work with, total valence electrons that you have to work with, and then you can arrange things however you want that gives everything a full valence. So rather than starting with the sulfur having 6 and each oxygen having 6, that's not going to work as well. It's not going to be as easy to see what the combination is. If you just say, I have a total of 24 electrons to work with, and I need to fill up everything. We'll keep practicing with it.
Yeah, like I said, I would have started with us, and I would have done, whatever. And then I probably would have put the O here, and then I would have realized that there's nothing sharing enough electrons.
It gets even trickier because, put another dot there, that's actually what sulfur has 6 valence electrons,
Oh, right.
So it looks like that. So it doesn't even look like there's a place to put 3 oxygens, right?
Yeah.
So, but if you just say, well, I know that they have to be attached because it said it's SO3. So, and that to say, well, I have this many electrons to work with, I know I have to have sulfur in the middle and the oxygens around it. How do I arrange things so that everything is stable?
And there isn't just like a blank
Right,
2 electrons,
exactly.
not sharing.
Exactly.
Okay, all right. I guess. It's gonna take practice.
We'll keep practicing.
Yeah. Yeah, let's see that one.
So how many electrons do we have to work with?
16.
Total is 16, 5 from the nitrogen, 6 from each oxygen gives us actually already, so 5 electrons from the nitrogen, 2 times 6 electrons for the oxygen, plus, so that's 17 plus the -1 charge,
Wait.
a total of 18 valence electrons.
So, I figured it out.
So that's your nitrogen, like we just talked about, Jen.
Okay, so wait, so I've got 5 for nitrogen, I've got 6 for oxygen, and then times 2, and then plus 1 is 18. So now how are we gonna start?
Okay, so,
And in the middle.
and in the middle, because it's less electronegative. We know the oxygens have to be attached to it, right? Because otherwise it wouldn't be part of this formula. So we know we have to have the nitrogen in the middle, 2 oxygens. And we can go ahead and draw the first 2 bonds there as well, because we know they have to be attached, right?
Right.
So that gives us, we just used, out of our 18, we just used 4. We have 14 electrons left. And then I always start at the outside and work my way in. Whatever's on the outside is the worst sharing. So if you start by filling up all the oxygen's valences and see how many electrons you have left over, we're well on our way to making everything stable, right? So each oxygen still needs another 6 to be stable, right? So that used another 12, so we're down to 2 electrons left.
Oh, the long.
So one, put a pair on the nitrogen, now we ran out, right? And now we're down to no electrons left, but we still need 2 more electrons on the nitrogen for it to be stable. And you're exactly right. Anytime we have an empty space and we've run out of electrons, that means we've got to do a double bond. So pick one of those lone pairs and erase it and turn it into a bond. The trickiest thing is just remembering you have to erase one of the lone pairs you already drew. And like I said, we're going to keep practicing with this. Okay? What time did we start break? 5 till? Okay. Or at 2. We started at 2, huh? I said come back at 10 after.
I got
Oh, no. Twice.
I didn't know if it was a zero, so I don't know.
It's right here. I got it.
Yeah.
There's always good reception.
We had a snow day yesterday, so we weren't able to start on this.
Nice.
But I'd much rather have.
You could have just hopped on mine.
I mean, I get it,
Yeah.
but.
Same things, and I start to fill it out.
I mean,
It's all the same shit.
Five.
Yeah.
I should have just gone with the lab today.
You can absolutely do that. Especially since we're not a super full. Sometimes that's not an option because once we get to 24 people in a lab, I can't let more in for safety reasons. But we only have 24 total enrolled in the class. So as long as you let me know ahead of time so that we don't wind up with only one person showing up to lab on Mondays, then the Tuesday time slot is always an option for making stuff up, especially if we have snow days like yesterday.
And what time is the lab?
It's a half an hour earlier, so it's 10 to 12:30 instead of 10:30 to 1.
Okay. Hey, Sean, I might be there in person. Give me the heads up.
Okay?
Cool. It's just midterm review, right?
So you have one more lab assignment, but it's going to be related to these ionic or these molecular compounds that we're talking about.
Okay.
So it'll be more practice with Lewis-Dot structures and then applying that to get a geometry, a shape for the molecule. And that's the last thing we're adding this before the midterm.
But this part this is the actual practice. Look at it. Yeah, just count how many atoms or how many protons each of the lights.
Down.
And then there's one complicated question.
That's only midterm?
Yeah.
Okay.
So that we can just do energy of protons, ions.
Makes sense. Haven't done it, but that makes sense.
The answers are kind of, when I hear my die, it's double.
That was the one missing. I mean, you did talk. You do that.
All right, some quick practice before we go on to doing more Lewis-Dot structures. Let's go back to the nomenclature part real quick. Right, so the basic idea is you just say how many you have. Turns out with covalent compounds, there's more than one ratio that you can combine these in that will allow things to have, for everything to have a full valence or be stable enough that we can see it existing in the real world. So that's why we need these prefixes. With ionic compounds, we don't need these prefixes, right? Because there's only one whole number ratio that makes the charges cancel out. and with the Roman numerals when we're not sure about the charges. But if we have a covalent compound, there's more than one compound that's still just the same two elements. You can have N2O or NO2. So you can't just say nitrogen oxide. You have to say how many you have of each. So carbon dioxide is CO2. Familiar one, right?
Why wouldn't it be monocarbon dioxide?
This is why I picked this, because this is a really good example. We don't say monocarbon dioxide because I say otherwise, you're supposed to assume you have one of whatever you write first. Whatever that is least electronegative, whatever you write first in these formulas, you're supposed to assume that you only have one of those, unless, and if that's not the case, then you use a prefix. No. I know you're making a joke, but I'm going to not make that joke because we want to keep things straight and not make things more confusing. For now. Right? Too many exceptions. So carbon dioxide, you don't say monocarbon dioxide because you assume if there's no prefix, it's a mono. You don't just say carbon oxide because carbon oxides, plural, would be both carbon dioxide and carbon monoxide. Carbon oxides is the whole group. So we have to specify how many of those oxides there are. So carbon dioxide versus carbon monoxide.
Okay.
And I'm not going to mark you wrong if you write carbon monoxide. Typically we drop, if you wind up with two O's in a row because you put mono on it, you just drop one of the O's. So carbon monoxide, not monooxide. But I'm not going to mark you down wrong. Nobody's going to ever misinterpret. If you say carbon monoxide, they might look at you funny, but everybody's going to know exactly what you're talking about. Right. One that I will, so this would be dinitrogen monoxide. This would be nitrogen dioxide. Right? So get your prefixes down. And this covalent compounds are actually really easy to name. Say how much you have of everything. Carbon monoxide. Nitrogen dioxide. Dinitrogen monoxide. Carbon dioxide. The trickiest one to remember up till you get to octa anyways, is tetra. That seems like that should be quad or something, right? In Greek, tetra means four. It's actually where Tetris gets its name. The game Tetris, every piece in the game Tetris is 4 blocks put together.
Oh, yeah.
And if you manage to get one of those long, skinny pieces 4 in a row and clear 4 rows at the same time, that's called a Tetris, because you cleared 4 rows at the same time.
Ah.
So tetra and Tetris, should be able to remember that.
Okay. Second best-selling video game of all time, too.
Somebody found a copy of the NES version and at a garage sale and gifted it to me because I used this as an example, and they didn't have an NES anyway. So I have a copy in my office of Tetris for NES in a box. Never been opened. Patty, do you have a question?
Is Tetra
That's the tesseract. A tetrahedron is a 3-sided pyramid, but if you count the bottom of that, that's actually 4 sides. So a tetrahedron looks like...
It's a triangular pyramid.
You just can't see the backside.
You just can't see the backside. So that's a 4-sided object where every side is an equilateral triangle. And so that's called a tetrahedron. Hedron means sides. So if something is tetrahedral, it has this general shape to it. We're going to get into tetrahedral objects pretty quickly. Hepta, the rest of these I remember hepta is different than septa, but they both have the P in them. I don't know, for whatever reason, I always had these kind of memorized in the back of my head, and I remember being like a 4th grader and realizing that there was names for different number of kids somebody has. So there was like triplets and quadruplets and pentuplets and hextuplets and septuplets,
Octomom.
and octuplets. So all of those things, that's how I remember first learning it. Is like, oh, we have these prefixes that just mean how many you have of something. That's kind of cool. I was a nerd even as a kid.
You mean you were
But-
cool as a kid?
There you go. Being a nerd is cool these days, right? Science is the new rock and roll.
Back then too, but most people don't.
Sean, because you put in those two conveyor bonds in that order, like for the nitrogen dioxide, if you just switch, could you swap them, or is there just an unwritten rule somewhere that
The
nitrogen
rule
will
for inorganic nomenclature is that you're supposed to put the most electronegative element goes last. So the closest to the top right here goes last. So oxygen is always going to be after everything except for fluorine. Right, so yes, there is a rule for what order you put them in for that reason.
Are there exceptions to that rule?
Not till you get to OChem.
Okay.
Occasionally, when we're dealing with structural formulas, it makes sense to put them in a different order. But not for right now.
Just for that CF2,
Right, so
CF2.
that's written as the way an organic chemist would write it, CF2Cl2 is written that way. Even organic chemists would probably usually flip those two, and then it still follows our rules. But we wouldn't even name this with the same system, because as soon as you get 3 nonmetals at the same time, then we don't use this system. There's going to be another way to name that. That's based on how many carbons there are and how the carbons are arranged.
Wow, no way this will ever confuse me.
Right, so we added on a little bit at a time, and why context matters a lot in chemistry.
Yeah.
Are we gonna kind of stay away from hydrogen for a while? Because that's where things get a little different, right? Like glucose, for instance, the H is just in the middle there.
It is, yeah, so we'll stay away from hydrogen when it comes to naming these things, for the most part. All right, so when we look at these nonmetals, there's one other aspect of them is when we have pure elements for the metals, they're all neutral, right? And so they just kind of like hung out together, even though they have some extra electrons. And that's what actually makes them have good conductivity, is all of these metals, when they're neutral, have extra electrons they don't really want. Which, in those extra electrons, they can shift wherever they need to get to be most stable. So you can move electrons a long way, one direction or the other direction. But nonmetals don't do that. Nonmetals are trying to gain electrons, right? So nonmetals actually will make covalent bonds with themselves when they're a pure elemental substance. So all of the elements that are in yellow are what are called diatomic elements. When they're in their pure neutral state, they actually exist as molecules, not as individual atoms. Because if you put a fluorine that has 7 electrons in its valence, it has 1 empty spot, right? Right. You put that next to another fluorine that also has an empty spot. Both of them can be satisfied if they share electrons, right? That's the whole premise of covalent bonds, is share electrons so that everything can have a full valence. So all of these nonmetals, that when they're in their pure state will turn into these small molecules. So fluorine, when it's pure fluorine in its elemental state, is just F2, not just F by itself. Chlorine, Cl2, hydrogen H2, oxygen O2, nitrogen N2. All of the ones that are yellow here exist as these diatomic molecules. The ones that are labeled in pink here, they're called polyatomic molecules, but they're a lot more complicated, and I'm not going to make you memorize what those formulas are, because a lot of times it's more than one anyway. So the difference between red phosphorus and white phosphorus and black phosphorus.
But there's black phosphorus?
There's black phosphorus is basically how big these little structures are that they turn into. And sulfur can exist as S4 or S8 or S12 in its pure state. So I'm not going to make you memorize those ones. Carbon can exist either as graphite which is, pencil lead.
It's got a bunch of different forms.
It's got a lot of different forms. So the most basic ones are diamond and
Graphene.
Graphene is just one version of graphite. It's a
Okay.
subclass. But basically, you get all of the non-metals will turn into these complicated structures when you have them in their pure state, because they wind up just making covalent bonds with each other. It's still considered a pure element because there's nothing else there. And it's still neutral, so it's not an ion, but it's a molecule. It's a covalent compound made of only one element. And so the diatomic ones are the simplest ones. For most of the rest of these, for carbon and phosphorus and sulfur, we just treat it like it's a lot like a metal, where in its elemental state, you just write P for phosphorus. But for oxygen, you specifically will write O2. Or if we're doing nomenclature, if I say oxygen or oxygen gas, the formula for that is not O. The formula is O2. All right?
So if we're doing Lewis-Dot structure, what's the difference in the dot structure between oxygen and sulfur? I mean, it's in the exact same column, so it has the exact same valence electron. So why is that
The
different?
difference is the size, and the size changes how many bonds it can make with how many things around it. If you tried to link up a bunch of oxygens into one larger molecule, you wind up with a bunch of oxygen-oxygen single bonds, which are actually reactive when you shine UV light on it. That's what a peroxide is. It means that you have an oxygen-oxygen single bond, and when you shine light on it, it splits up into radicals, to unpaired electrons, which are really, really unstable. They're radical. It's awesome.
Nice.
I have no idea why they chose that name or how it turned into a symbol of search culture, but it did. So now you will all remember it. So basically, but sulfur doesn't do that. Sulfur single bonds are more stable, and sulfur themselves are bigger because they have the extra energy level.
Okay.
So sulfurs can link up into these more complicated shapes, but oxygens can't, just based on the sizes.
Because they're just in an energy level lighter.
Exactly.
Okay.
This basic also gives us one more way we can split up our flow chart of what something is. So actually, before we had pure substances, we had all matter up here, right? And all matter could either be a pure substance or it could be a mixture, right? And then within mixtures, there was homogeneous and heterogeneous. Within pure substances, there's elements or compounds. Elements meant you just had one element, and compounds meant you had more than one element mixed together, but always in the same ratio. So compounds can be split up into ionic compounds or in the molecular or covalent compounds, right? We added that differentiation today. Elements can be either atomic or molecular. That's those diatomics that we just added. All the non-metals besides the noble gases are going to be molecular elements. The ones that are most important are the ones that were in yellow, or the diatomic ones, which is column 17, oxygen, nitrogen, and hydrogen. Basically, all the ones that are gases at room temperature that aren't a noble gas. Remember, those are always our exceptions because they're foreign. Chlorine and fluorine are also gases at room temperature. Bromine is a liquid at room temperature, and iodine is just too big, so it's a solid. But that whole column are going to be diatomic when they're in their pure elemental state. All right, so when it comes time to practice naming these, the big key is it ionic or covalent? Once you know it's ionic, you just say the name of each ion. Once you know it's covalent, you use those prefixes. That's our main clue for differentiating between the two. So for this one, I'm not specifically testing you on can you tell the difference. These are all covalent, right? They're all molecules because they're all nonmetals. So naming them, just use those prefixes. We already did CO, which is different than CO, right? because that's cobalt. That's carbon monoxide. Silicon
Tetrachloride.
tetrachloride. Triiodide. So this one we don't drop the double in this case. It is triiodide, which you wind up with more vowels than seem reasonable.
Wow, that seems really weird.
Triiodide.
Why not triiodide?
Not triiodide.
Triiodide.
It feels wrong saying triiodide for some reason.
Yeah.
It does. When in doubt, don't go with your gut when it comes to nomenclature. Just please don't say it sounds wrong. We're gonna get to the point where it sounds more natural, but you're not there yet. Go with the rules.
Tetranitrogen.
Have the rules down.
Tetrachloride.
Tetranitrogen tetraselenide.
Oh, gosh.
N4SE4. Tetranitrogen tetraselenide.
I feel like we're speaking gibberish for some reason.
A little bit. When some of them are really weird because like Te, right underneath selenium is tellurium, right? If you have say, this is a compound that gets used in solar cells sometimes. That's cadmium, right? It's an ionic compound. The name is, that's cadmium. When tellurium has a negative charge, you drop the end and put ide, right? So what does tellurium become? Telluride, like the town in Colorado. I don't think that's where the town in Colorado got its name, but it might be actually. I can be pretty sure that tellurium was not discovered there because there's nothing in Telluride other than a ski hill, right? I don't know if any of you have been there, but it's a pretty small town. So Cadmium Telluride is the name of this compound. So it sounds really weird when your name is the name of a town, but that is the proper name for that compound. Going the other way is even easier, right? And here's some test taking strategy. After you do the part where you come up with the name, and you look at the part where I give you the name and you do the formula, use this as a clue to remind yourself, because I'm probably going to put similar stuff but backwards down here, right? Like, oh, I forgot I'm not supposed to put mono in front of things because none of these have mono from the first one, right? Like, oh, I can't remember what 4 is. Look down here and see if anything jogs your memory. Look down at these ones and say, oh shoot, I was supposed to use Roman numerals on half of those ones up above. Right? So use the test as part of your reminders. The test itself will help you take the test if you look at it the right way. Sort of thing that always seemed kind of like second nature to me, but I realized that I instinctively take tests differently than other people. I wasn't going to say that. I don't know how you guys are at tests yet, but Jordan, did you have a question?
Oh no, I was going to say the next one.
Okay.
PCl3.
PCl3.
ClO.
ClO.
That's
Disulfur tetrafluoride.
S2F4.
Disulfur fluoride, and there's 4 of them. S2F4. Phosphorus pentafluoride.
Pf5.
Pf5.
Take that, Jordan. The only way I know if I know science is if I get to the answer before Jordan.
Well,
No. I
Do it,
should be
I'm
your.
ready.
Honestly, I should probably be your true self.
That's true.
well,
So I
we're
guess
not
I'm
going to get into
wrong
the psychology
all
of
the
that.
You don't have to.
But
1 second.
so don't second guess yourself too much on these. Get those prefixes down, and then be thinking when you're down here. Think about what you wrote a second ago, right? Right. Follow the rules and don't think about it too much.
Don't think about it.
All right.
Trust your gut.
Don't think about it. Don't trust your guts.
Don't do too much.
All right. So Lewis-Dot structures we've talked about a little bit. Here's our steps for writing Lewis-Dot structures. Determine your total number of valence electrons. Figure out what goes in the middle. Usually that's going to be whatever is the least electronegative goes in the middle. The exception being hydrogen, because hydrogen can never be in the middle. Because how many electrons does hydrogen need to have a full valence? Only
One.
2, right? It only needs to gain 1, have a total of 2. So that means at most, hydrogen will only ever make 1 bond. So if it can only ever make 1 bond, by definition, hydrogen can't be at the middle. You can't be our central atom because it's only making 1 bond. It has to be at the end of a chain. Right? So hydrogen will never go in the middle. And other than that, whatever is least electronegative is going to go in the middle. So in this case, oxygen is more electronegative, but it has to be in the middle because hydrogen can't be. Right, so when we're drawing these, we figure our total number of valence. These can be in any order, really. It doesn't really matter what order you find these. What happens next is that we're then going to arrange them so that everything has a full valence. Right, so counting total valence electrons, hydrogen brings 1 electron each, right? And there's 2 of them. So 2 times 1 electron. Oxygen, we have 1 oxygen and it brings 6 valence electrons. That only gives us a total of 8. So now we're going to figure out what atom goes in the middle. We just went through that. It can't be the hydrogen, so it has to be oxygen.
Yeah.
There are other clues that are not hard rules in terms of there will be exceptions to them. A lot of times, whatever you have 1 of is going to be in the middle. That's not always going to be the case, but it's a kind of a clue. The rule that you always want to follow is hydrogens can't be in the middle, and then you put whatever's least electronegative in the middle. All right, so in this case, oxygen goes in the middle, hydrogen around it. We know the hydrogens have to be attached, or they wouldn't be part of the formula, right? So we can use 2 of our pairs of electrons to do that. Now we don't have 8 electrons anymore, we have 4 electrons left.
A line means 2.
A line is a pair of electrons. Essentially, we're only going to be dealing in pairs of electrons. Unpaired electrons are radicals that are extremely unstable. And that's not a political statement.
So they have a short.
So we're only dealing in pairs of electrons, basically, though. So that means bonds are going to be pairs. We have 4 electrons left. Hydrogens are both already filled, right? Normally what we do is start at the outside and work your way in. The hydrogens are already filled because as soon as they make 1 bond, their first energy level is full. So we have 4 electrons left. Oxygen needed 4 electrons. So we had 2 lone pairs. All right, so this is where the Lewistop structures is helpful. With metal ions, ionic compounds, Lewistop structures are basically worthless because it doesn't tell you anything the charge doesn't tell you, or that the electron configuration doesn't tell you. Right, so, but with covalent compounds, they tell you what's connected to what and how. There was a question. Did you raise your hand, Reb? Did I answer it? Okay.
Actually, you know what? I'll just ask you.
Okay.
For the hydrogen, because it's now a line, you said there's a pair,
Mhm.
but hydrogen only has 1 valence electron. Because if those were just dots, then I get why there's 8 dots around oxygen. That gives each hydrogen 2, which that's not making sense to me.
So if we say that the black electrons came from the oxygen and the red came from the hydrogen,
Okay.
they're each giving 1 electron to make a pair
Oh,
to
okay.
fill up one of those
So it's just the
energy,
number
one of
of
those
electrons
orbitals.
in between the 2,
Right.
not the actual. Okay.
Exactly.
Yeah. That makes more sense.
It's easier to draw them as a line than as pairs, and basically representing the 2 electrons that fill up an energy.
Okay.
A
So if on
suborbital.
our test we only use dots and we don't use lines, are we technically wrong?
No, not for now. It'll get to the point where, like,
Okay.
because those complicated organic structures I was drawing,
Uh-huh.
all of those lines represent a pair of electrons. You would never draw something as complicated as benzene with dots,
Okay.
right? So it's not that you're wrong, it's just that that's not a habit that's sustainable long-term if you take any more chemistry.
Yeah, I bet benzene would be obscenely complicated with dots.
It starts getting very complicated when you start trying to use dots. Right, so here's our primary criteria. If you did your Lewis dot structure right, you have the right number of electrons, and everything has a full valence. If you can say yes to those two things, that's a valid Lewis dot structure. It might not be the most stable Lewis dot structure, and we'll talk about how to evaluate that, but it's a valid Lewis dot structure if you can say yes to these two things. And this is an order of importance. No matter what, you have to have the right number of electrons because we can't make stuff up out of nothing. And then if you're using the right number of electrons, the next most important thing is that everything has a full valence. There are some compounds where you don't have full valences, but there's nothing you can do about it. For instance, BH3, boron trihydride. There's only a total of 6 valence electrons. So how do you get a full valence for boron if there's only 6 valence electrons? You don't. You can't make up electrons out of nothing. Right? Because boron only has 3 valence electrons and each hydrogen brings 1 electron. So that's a total of 6 valence electrons. There's nothing to be done there. No double bonds that we can make because there are no more electrons. So in this case, the Lewis dot structure doesn't meet our second criteria here. But there's nothing we can do about it.
Can we go over P at Pf5?
Yes.
Because it's not looking at the density.
Okay. We'll get there in 1 second.
Yeah, no worries.
All right, so there was a bunch of practice problems for Lewis dot structures that we're going to skip over for now. Sometimes there's more than one possible Lewis dot structure that satisfies our criteria. Remember, our criteria are use the right number of electrons and then, when possible, fill all the valences. Well, both of these structures, so this would be for the formula C or H2CS. Both of these structures fill our criteria, right? They have the right number of electrons. Everything has a full valence. So how do we know which one's right?
The one that is less electronegative goes in the middle, right?
The one where least electronegative goes in the middle. And the way we quantify that is by looking at how many bonds something has relative to how many electrons it started with. So it's what's called formal charge. All right, so formal charge is the idea that it's just like, in a lot of ways, it's just like charge, the way we've been looking at it. How many electrons does something have compared to what it started with? With formal charge, we're not saying there's actually a charge on these atoms. The overall structure is still neutral. But if we compare the number of protons or how many electrons something has compared to where it started with, we can get an idea of which of these is more stable. So formal charge compares the number of electrons to the electrons the atom started with. It's defined as the valence electrons in an atom, so when it's on the periodic table and it's neutral, minus how many electrons it quote-unquote owns. How many electrons does it control in this structure? So what does that mean? That's kind of a weird term to use, considering property is probably a foreign concept to atoms. We're looking at every atom or every pair of electrons that's shared. Each atom really only owns, quote unquote, half of those electrons, right? Half the time they're next to the sulfur, half the time they're next to the carbon. But anything that's a lone pair that's not part of a bond, that atom owns it outright. So it's a little bit like, I always use the example of buying a snowmobile. Buying one snowmobile is not very fun, right? You really want two snowmobiles. Otherwise, you have to share your snowmobile when you're out snowmobiling with people, right? If you bought a pair of snowmobiles with your friend, how many snowmobiles do you own?
One.
One on average, right? Sometimes you have two snowmobiles, sometimes you have zero snowmobiles. Right, so these shared electrons, the electrons that are being shared between carbon and sulfur, the sulfur owns half of them, the carbon owns the other half. Right, so what that allows us to do is say, okay, well, carbon now has 4 bonds around it, right? If it has 4 bonds in this structure, then it controls, so this is a double bond between the carbon and the sulfur there. It controls half of those, and half of those, right? That's a total of 8 electrons that it owns half of. So it really, the carbon owns 4 electrons. And when carbon's neutral on the periodic table, how many valence electrons does it have? 4. So if carbon in this structure owns 4 electrons, and on the periodic table it has 4 electrons, it has a formal charge of 0, because it has the same number of electrons that it owns. Let's look at the reverse one. We're still just going to look at the carbon. If we change it so that it's set up like this, so this is the second structure here, how many electrons does carbon, how many electrons is it sharing? Sharing a total of 4, right?
Yeah.
And each of those count for half. So half times 4 electrons. And these lone pairs, though, it's not sharing those with anything, right?
So it owns 4.
So it owns those outright.
Yeah, so plus 4, right? So plus an actual 4.
So that gives us a total of 6 electrons owned in this structure, right? Because it's got the 4 that it owns by itself, and then it's got the 4 that are shared. So in that case, if it owns 6 electrons, and on the periodic table, carbon only had 4 valence electrons. It has 2 extra electrons now, right?
It has a higher formal charge.
It has a higher formal charge. So that the carbon here would have a formal charge of -2. Yeah, because it has 2 extra electrons. What about, and here, the carbon was 0. What about the sulfur in both of these cases?
Sulfur is supposed to have 6.
Sulfur is supposed to have 6 when it's neutral, and here, it owns 6, right? So 6 electrons owned. So in this one, the sulfur also has a formal charge of 0. Versus if we switch the 2, carbon has a -2, and in this one, sulfur, it only owns 4 out of the 8 now, right? So plus 2. Here's our third criteria for, is this a good Lewis-Dot structure? 1 was use the right number of electrons. 2 was fill all the valences. The third most important is keep your formal charges as close to 0 as possible. Formal charges of 0 are more stable than non-zero. So if we're choosing between these 2 possibilities, this one is more stable because this has formal charges of 0 for both of these atoms.
Why would the charges not cancel out if one's plus 2 or
They do to give the entire overall molecule a charge of 0. But what we're doing here is basically putting numbers to the idea that what's most electronegative should go on the outside. whatever's least electronegative or has the most vacancies, most open spots in its valence shell is usually going to go in the middle, because that's what gives it the lowest possible formal charge. All right, so let's do a practice with that to answer one of the questions on the practice test as well. Pf5, phosphorus pentachloride. So, if we start by counting our electrons, each fluorine brings 7 valence electrons, right? And there's 5 of them. So 5 fluorines, each that brings 7 electrons. Phosphorus brings 5 on its own, correct? 1 phosphorus that brings 5 valence electrons.
So 40.
40 electrons total. We're going to put phosphorus in the middle because it's less electronegative than fluorine. So, we wind up with something weird. If there's 5 fluorines attached to a phosphorus, we wind up with more than 8 electrons on the phosphorus.
Yeah.
But the formula says they have to be there, right?
Isn't fluorine one of the ones that can be like,
It is, fluorine is diatomic, but if we say that the formula is Pf5, then that means we're saying that all 6 of those atoms have to be attached somehow. So in theory, we could have something that looked like that, but we'll talk about why that's not a good solution in a minute. I did tell you that was wrong earlier. So we just used 10 of our 40 electrons, right? 2, 4, 6, 8, 10. We have 30 left. How many does each fluorine need?
6
Each fluorine needs another 6, right? Which 6 times 5 is 30. So that's going to use up all of our electrons now. It gets a little tedious, especially when you're watching me do it and not even doing it yourself. I can hear the eye rolls. It's a parent thing. When we do this, we use up all of our electrons. That satisfies criteria 1, right? Number 1 criteria, use the right number of electrons. Criteria 2 was fill everything's valence.
Even if it's overfull.
Our fluorines are all good. Our phosphorus looks weird. But phosphorus is in the 3rd row of the periodic table. And what happens when you get to n equals 3?
So it's
Another orbital type after P, right?
D.
Once you get to n equals 3 to the 3rd row of the periodic table, there's a d orbital, even though it's empty. Phosphorus has an empty d orbital, so it can actually go up more than 8 electrons because it has that empty d orbital. Nothing in the 2nd row will ever do this. But if we look at the formal charges for these, fluorine, how many electrons does each fluorine control now?
6. It owns 6.
It owns 6 outright, plus it's sharing another pair, right?
7.
So each fluorine has 7 electrons, and what does it have on the periodic table when it's neutral? 7. So each fluorine is neutral, which is good, it's stable. Each phosphorus, the one phosphorus, how many electrons does the phosphorus own?
5?
It's got 5 bonds, so it's got 10 electrons that it owns half of. So 5 electrons owns, how many does it have on the periodic table?
5.
So the phosphorus actually has a formal charge of 0, even though it has extra electrons. There's extra bonds.
It doesn't really have extra electrons.
It doesn't have extra electrons, yes. It has, what it has is more bonds than we would normally think is stable. Because normally we think of get to 8 and you're good, right? Phosphorus can have more than 8 because that's going to give it a formal charge of 0, and it has that d orbital to work with. If we try the other possibility that you might think of, which was to attach one of these fluorines to itself,
You have more electrons than you started with.
the other pair of electrons winds up having to go right here, right? You still have to find a place for another pair of electrons. You still have to use the right number of electrons, right? So you still need it to add up to 40. And if you do this, you still have a total of 10 electrons around phosphorus, but now it owns 2 of them outright instead of being shared. Which means it owns 6 now instead of 5, right? So 6 electrons owned gives phosphorus an overall -1 formal charge. And this fluorine owns 6 and it wanted 7. So the fluorine gets a +1, the phosphorus gets a -1. Both of our formal charges are farther from 0. This is less stable than putting all 5 fluorines around phosphorus.
And that's how it would act in nature.
Correct. It's still going to be a pretty unstable compound. It'll react with something, but it's more stable than this. And it's more stable than having fluorine by itself.
Is there, I mean, I was gonna say, is that kind of coincidental that with the 5 fluorine pair, like with the 5 pairs of electrons, that comes out to be 10 electrons orbiting, and it's also, I mean, and then, but we're also in a D, which is contains CO2.
So that part is coincidence. What's not coincidence is that the formal charge can go to 0. Anytime you can arrange something so that the formal charge of every atom is 0, that's probably a stable enough compound that it will exist. It might not be common. It might still be unstable, but it'll exist. And so the fact that that we can arrange it so that everything has a formal charge of 0 is not coincidence. The fact that it's 10 instead of 8 or 12 is coincidence in this case. It's not related to how many electrons a d orbital can hold. But I like where you were thinking. All right, we're out of time. We'll do practice with this and shapes of molecules and review. So we'll have like 8 slides worth of new, actually we'll probably cover it in lab tomorrow and on Thursday, and then Thursday's lecture will be review.
And this is today, right? But we didn't have to do this part, as you said, we had to do with the electronegativity.
Yes, that's fine. Yeah, we'll get it. That is what I said.
Right.
Do today,
This is it.
Yep,
Yes.
I'll take it.
in the lab.
In the lab, yep.
And what part do we not have to do after that?
The electronegativity part.
Oh, thank God, yeah, we just placed it with the ionization energy, right?
Right.
Do we have access to the
Practice? Yes, yeah, it's on Canvas. If you need a printed copy, you can go to the library, print it out, or come see me in my office. Okay? No problem.
So for the promise program, I have to.
Well, at least we know where the other
Yeah, that's fine, because we haven't had midterms yet, and you're gonna do well enough on the test, it's not gonna change your grade from an A anyway.
Thank you.
No problem.